You may have worked with this kind of cipher when you were a kid on your like kids workbook and stuff like that, and you would encode something like "send me money" as S is W, right? And then send E is I, N is R, D is H. So this is really send encoded. Okay? So if you do this, it's send me money. Yeah. Have you done things like that? Yeah. So this kind of encryption is called Caesar cipher. I don't know how to spell Caesar. Is it like that? Caesar.
I think it's
C.
I think it's C
C.
E.
C-A-E.
Hey,
Oh.
no I.
Oh, okay. Caesar. Okay.
Might be wrong.
Right. No, I think that's right. Caesar. Yeah.
Yeah.
Yeah. So this is called Caesar cipher. Most primitive type of encryption there is. And you could think of this encryption as rotation by 4, right? Or rot 4, because like you go 1, 2, 3, 4 steps. So A becomes E, B becomes 1, 2, 3, 4 step F, B becomes F, and stuff like that. And therefore, if you want to encrypt, you have to go 4 letters towards this direction. To decrypt, you have to go 4 letters that direction. One popular version of the Caesar cipher is rot 13, because there are 26 letters in the alphabet. If you do going this way 13 and going this way 13 are the same thing. So if you know how to encrypt, just run the same encryption twice, it will decrypt the encoded message. So that's called Caesar cipher. Now you might wonder how encryption is done with more sensitive data, right? But it's really just this kind of idea on steroids, like, and the way it's done is instead of just one letter, if you do 2 letters and do something like this at the same time. So let's say AB is changed to CD, but AC is changed to something completely different, something like that, right? If you do that with every 2 letters, then it's harder to figure it out, right? And what's done is, so standards like AES 256, which is the standards that are now used in whenever you're browsing the web, you notice that when you browse the web, it's usually HTTPS, right? It's a secure connection. Very few websites are unsecure these days. And these days, if you log into any website and if the messages that you're going back and forth are unencrypted, they have this little icon that says insecure, unsecure, something like that, right? It gives you a warning. So when you have encryption, what's happening is that you're most likely using this AES 256 standard, which means like it's 128 bits. So what's that? That's 8 times 16. So it takes 16 letters, or 16, yeah, about 16 letters at a time, and doing changes. But then the encryption the encryption key. So this number right here, you can think of this as a key. If you know what this number is, then you can encrypt and decrypt, right? Yeah. Same thing. This is a key. So the encryption key will change like at every block. There's a pattern to how they choose the encryption key. So that makes it really hard to see what's going on, right? So these are the way people are encrypting things. However, there's a fatal flaw to this, which is that if somebody knows how to encrypt the message, then they also know how to decrypt the message, right? Yeah. Anyone that knows how it's encrypted will know how to decrypt. Right? And because of that, several uh, strategies were used to do this during the time of war. During the time of war, it's really important that you secure your weapons positions and your forts position, secure your plans, secure your communication. That was all important. So every message between different battalions were passed with some sort of encryption. And for that to be efficient, there are many ways. One was they would use something called a one-time pad. How many of you heard of one-time pad? So if you go to Washington, make sure you go to the museum for. There's a museum for these ciphers, different ciphers, and you can see some of the one-time pads that World War II soldiers were using. It's a small notebook where for each day they have the numbers that they use. Okay, and then once they use it, they rip it out and throw it away. Okay, so you keep using this, and they have different keys for different dates, so that even if the enemy figures out what the key for that day is, they wouldn't know what happens afterwards. That's one-time pad. Another one would be to send one brave soldier to like hide and sneak, go through the enemy territory and connect with the other folks out there, just to hand this key. Uh, that's the problem. But then now in the age of internet, you can never be sure if there's a hacker that's always listening to your connections, which actually is true nowadays. Yeah. There's always some bots listening to every connection that you make. So such a channel is called an unsecure channel. So there's an unsecure channel where the information is going back and forth between two people, A and B. Now, in many of the security literature, usually people call A as Alice and B as Bob. Yeah. So if Alice and Bob trying to establish a connection that's not secure. So there's this problem of how to communicate so that you can establish a secure connection. I mean, once you somehow can pass the secret code from one place to the other without any hackers fetching the data, then you can use the encryption standards to make sure that even if they listen to what's going on, there's no way for them to figure out what it is. It's like impossible to break AES 256 just with small amount of message that's passed on to each other. It takes a lot of computational power as well. Yeah, so here's how one might establish a secure connection between Alice and Bob in an unsecured channel in a hypothetical scenario where Alice and Bob lives in two different countries, and there are people that can transmit messages from one person to other. And this is not exactly same as the today's real topic, which is Diffie Hellman key exchange. This is what I'm trying to get at. Is it 1L or 2L? I don't know. Okay, so I'm going to be eventually going on there. It's a bit different, but it's still a nice story to think about. Let's say Alice and Bob are spies living in two different countries, and they need to communicate securely. And to do that, they need to figure out how to exchange the key so that later encrypted message can flow through. So what they do is Alice will write down the key on a piece of paper and try to send it to Bob. But the problem is there's no way to trust the person that's transmitting your message, and frankly, you can't tell them that you're a spy, right? So there should be a way to make this work. So what she does is she takes a briefcase, okay, and puts the key in there and locks it with her lock, okay? But she does not send the key with the person because then that person can open it, right? So the briefcase with lock on it is sent to Bob, okay? Now, there's no way for Bob to open the briefcase, right? And so what does Bob do? Bob takes another lock and puts his lock on it. Okay, now the briefcase has two locks. And that briefcase is sent back to Alice. And what does Alice do? Alice will open her own lock, right? And send to Bob the briefcase with only Bob's lock on it. Okay. Now Bob can freely open that lock, and he can open the briefcase to find the key. Makes sense, right? Yeah. So although it's kind of complicated, it has to go through back and forth 1, 2, 3 times in order to do the key exchange, but it's worth it, right? By doing it this way, even if some of the people that are doing this work, transporting the briefcase, are compromised, they might have received $1 million from the Russians or something. Alice and Bob can still trust that this is true, right? Oh, by the way, there's a totally unrelated to this discussion, a kind of attack that's nice to do in this scenario. There's something called man in the middle attack. And what happens is, like, there's this one person who knows that Alice and Bob are trying to exchange keys. Okay, they found out some information that these two people are going to exchange keys. So what this person is going to do is he's going to buy an identical briefcase, okay, and be here and pretend to the person that's transmitting that this person is Alice, no, Bob, okay? Do the key exchange, right? But then once it's done, he will pretend that he's Alice and talk to Bob and do the same procedure, okay? Now what's going on is, like, they've exchanged keys thinking that the whole process went untainted, but actually there was a man in the middle that was doing all this, okay? So there's always this danger of man in the middle attack. And the man in the middle attack is also possible in the Diffie Hellman key exchange as well. You'll see later. Okay, so that's another problem with these. Okay. Diffie Hellman key exchange was invented in 1976, and shortly after 1977. RSA, this is it's not a key exchange scheme, although it can be used for key exchange. This is an encryption scheme. So these are very efficient, and if any of these were invented during World War II, then the free world would have had a horrible time trying to defeat the Germans. Because the Germans had this machine called Enigma machine, right? Yeah, and then
Watch that movie,
well,
Imitation.
imitation game, right. So the imitation game is the game that revolves around trying to break that Enigma machine because that was really hard to break. They had a machine that would like rotate things around. It was very complicated, and only by getting a copy of that machine, they were able to see the inner workings and figure out what might be going on. Uh, yeah, but all those were during World War II. All the encryption schemes were symmetric, meaning that if you know how it was encoded, then you can decode it. But now let me show you the wonderful idea. Both of these are using modular arithmetic, and let me show you the wonderful idea of this. Okay. So, Diffie Hellman, they came up with their paper in 1976. Uh, does the following. So, Alice and Bob are trying to do a key exchange. They want to have a common key to use for encryption. Now, there will be, Alice will send to Bob some N and A, two numbers. And remember, this is going through a unsecured channel, so once Alice sends these two numbers to Bob, they just basically have to assume that it was compromised. People know what those numbers are. And they don't even try to hide it. Okay? It's out in the open. Okay? Now, what Bob does is this N will be used for mod, and this A will be used for the base. Okay. So what Bob does, Bob chooses a secret number B, and let me use a different color, B, because this is Bob's secret. This is not sent to anybody. Okay. And using this B, computes A to the Bth power. Okay. And mod it by N. You get some number, right? Yeah. So let's call this P. And then that P gets sent. That number gets sent. And Alice has her own number, secret number A. Okay. And Alice is going to take, I can't say A, sorry. The A is used for this. So let's just say C. So secret number C. And Alice is going to send A to the Cth power, modded by N, and say that's Q, and then Q is going to be sent. So N, A, P, Q are all public. Okay, everyone knows what those numbers are. Okay, but here's what B does. B will take Q, okay, and calculate Q to its own secret number B, right, and mod N, and it's going to end up giving you some K. Okay? And then Alice is going to take P and take the power of C mod with N, and she is going to get the K. Now, surprisingly, what's going to happen is that these two numbers will be the same, okay? And it will be really hard for people with just NAPQ to know what those C, B, and K would be. Now, after the key exchange Bob still doesn't know what C was. Okay. Alice still doesn't know what B is. But they would have a common K to use as encryption. Okay. Now let's see why this is true and why it's hard to figure out the hidden numbers C, B, and K. Okay? So first, question one, why are P, C percent N and Q, B percent N the same? Well, if we do the mod algorithm, it's obvious, right? So see, A to the B is congruent to P mod N. Is that right? See, they're the same. They have the same remainder if you view it in mod N, right? Therefore, if you take P to the C, P to the C, that's going to be same thing congruent to A to the B of C, right? Because P and A to the B are congruent, so I can replace P by A to the B. But that's going to be equal to that's going to be congruent to A to the BC. And that this is what the value of K would be. And this is what Alice would be computing, right? This is what goes. So Bob does this, and Alice would get this. And Alice would have K. On the other hand, when Alice computes A to the C and names it as Q, this is mod N, right? And then you have Bob receiving this number Q and taking it to the Bth power, but that's same as A to the Cth power to the B power, which is same as A to the C times B. But look, C times B is same as B times C, right? So you end up having the same number Q. Now, it might be a bit hard to understand since we haven't used a concrete number. So let's try to redo this using an actual number. So let's say N is 11, A is 2. Now usually what happens is that this N would be a really big number, okay? And this number would be usually small. What I didn't explain is that this number has to be something called a primitive, but let's not go about that. I think, yeah, it's some small number, okay? And then let's choose, for Alice, let's choose 3. Oh, let me use a different color. Let's use 3 for Alice and 4 for Bob. Okay? So, what happens? What does Bob compute first? 2 to the 4th power mod 11, right? 2 to the 4th power. So, because 11 is chosen, all the calculations we are doing will be in mod 11. 2 to the 4th power is 16, right? Mod 11, what's that? 5. If you subtract 11. So 5 is the number that gets passed to Alice. Okay. And then if you have 2 to the 3rd power, which is 8, and that's just 8. So Alice is going to pass to Bob 8. Okay. On the other hand, so now Ellis has this number 5, and Bob has this number 8. Ellis is going to take that number 5 and raise it to the power of her key, 5 to the third power mod 11, which is 125. Well, 121 is a multiple of 11, so this is going to be 4. So 4 will be the value of k that she is going to calculate. Let me write down this again, the proper color. 4, 4. And that's what Alice does. Okay, this is Bob, this is Alice. Okay, and then Bob is going to receive this 8 that he got from Alice and take it to the power of 4, because that's his key, 4. And what is that? It's, well, we can do it like this. 8 is equals to -3, right? 8 is congruent to -3 mod 11. If you subtract 8 minus 11, you get that. And taking the fourth power, that's 81. Well, 77 is the nearest number that's divisible by 11. So if you subtract 77 from it, you do get 4, right? So Bob does this. Now what happens? They have the same exact number to be used for encryption, right? And what do the public have? Public has these numbers, 11, 2, 5, 8. Okay. So if somebody's trying to hack this, how would they hack? They would think about all the possible pairs of numbers, right? And basically what this is, 2 to the what number mod 11 gives you 5. And 2 to the what number mod 11 gives you 8. So you have to figure out these numbers in order to figure out Alice's and Bob's key. In practice, right now, this can be solved by brute force, right? You can do all the numbers from C. We know that 2 to the 10th power is 1 mod 11 by Fermat's theorem, right? So since 10 is not, and you can try all the numbers from 1 through 9. That's not much. And then by doing that, you can figure out what these numbers are. Now, do you see the similarity of this question with saying something like 2 to the what power is 256? This is, without the modulo, in the regular math, you can solve this. What kind of math solves this? Log, right? The solution of this is, it's called log. It's log, this question mark is log 2 of 256, right? So this is like same as asking the log of 5 in mod 11 world. Yeah, log 2 of 5 in mod 11, okay? So these kind of problems are logarithmic problems. But if your prime number or whatever the number is, if it's like, say, 20 digits long or maybe 40 digits long, then even with the strongest computer, you can't go through all those numbers in time, right? Brute force becomes impossible. So that's why this thing works. Yeah. And once these keys are exchanged, then they have the AES 256 established, and that's what makes your web connection secure. So if you ever wondered, like, if hackers are always listening to what I'm doing, how are we connecting to the server to establish a secure connection? It's really the Diffie Hellman key exchange. Yeah. There are several versions of this. There's something harder than modular arithmetic. There's something called elliptic curve cryptography. That's another algebra system. Again, it has to do with the fact that forward problem is harder than backward problem. See, the reason mathematicians were able to come up with these kind of system is the following. See, everyone knows 1 plus 3 is 4, right? Finding that the value of this is 4, any kid can do it. But now, you take a 4-year-old kid who just learned how to add stuff, 1 plus what is equal to 4, that's a backward problem. That's an inverse problem, right? That's suddenly harder. Okay? And in math, there are tons of examples where the forward problem is a lot easier than the backward problem. And what people found out was that this is a key example. Trying to take 2 to the fourth power mod 11 is a simple problem to do, but asking 2 to what power mod 11 gives you 5 becomes suddenly very hard. And especially when you have a very big number, then it becomes impossible. Okay? So these type of cryptographic schemes are called asymmetric cryptography. One way is a lot harder than the other way. So these type of functions are called one-way functions. Calculating one direction is a lot easier than the other. And the modern cryptography is all based on that. Okay, so next time I'm going to explain to you the RSA encryption, and that's even better, right? So once you learn how these things work, then you kind of see why people are okay with like sending things on the internet if it's a HTTPS connection, and why HTTPS is so much more important than just an HTTP connection, which is not secured. Okay?